Okay, first thing we're going to do to build keras model is set one up. So how do we do that? Well, we're going to do what's standard, and that's sequential deep learning. Okay, sequential is the model. It's like nodes going in sequence left to right. And they're also going to be densely connected, which is what you saw in the slides where every node connects to every other. And this is also very standard. So to do that, we need to do the following imports. Okay, do this with me. From keras.models, import sequential. Okay, that's kind of like the main model, like logistic regression, but you also need this from keras.layers because you're in control of the layers as well. Import dints. Okay, those are the fundamentals that you need to actually build a model here. Now, to initialize a model, and I'm going to put comments in, so initialize model. I guess for this one, we'll call it just import sequential indents. It's just like before. So again, the model is sequential, so you can probably predict what the code should be. Go ahead and put it in. Try it on your own. In case you're not sure, just put in model equals and then sequential with regular parentheses, nothing added. Now, if you want to see, right, oh, what is that in keras? You just put in model after initializing it. You can see it just gives like keras.engine.sequential at some location. I don't know that stuff, okay? But it's just showing you kind of where it is. Okay, so how do we there's this talk about layers, right? And look, if you're not doing hidden layers, don't do deep learning. The whole point of deep learning is to actually have hidden layers. So we want hidden layers, okay? So what we're going to do right now is add a hidden layer. We'll start with just one, and then we can look at adding more. Okay, so the layers are densely connected. So dense is actually what you want to add there. Sorry, not model equals, it's model.add. Okay, we already have the model set up, but we're adding a dense layer, so dense goes in parentheses. Now, if a second open parentheses, go ahead and put that in. And you can see Google is sometimes helpful here where it says units, right? That's like the number of nodes, the number of circles. So that's kind of a fun one. I mean, look, if you're only gonna have one hidden layer, it's kind of up to you what you put in there, right? It has to do with how mathematically intricate you want to make the model, and you can ask yourself too, what's the shape of this? That can be helpful in determining this. So for instance, if I type in x.shape, I can see that I have 2,000 rows and 784 columns. Okay, that's a lot of columns. So I can tell you that generally speaking, dense layers range from hundreds to less. Okay, sometimes people make, say, long and tall hidden layers. Sometimes people make like more hidden layers that don't have as many nodes. There's not really a right or a wrong here. I think we can also note that most of our 784 columns are zeros with few ones. So, I don't know what the answer is. Pick something that you like. I'm going to go with like 80 today. I sometimes just do something different. And the point with machine learning, and I think in deep learning as well, you don't want to just go with some textbook like, well, this person said 80, so I'm always going to put in 80. Man, be flexible. Try things out. You want to experiment, okay? But that is your number of hidden layers. Now, in the first one, if you put comma there, it's standard to actually then set it up properly with an input, okay? And so what is the input shape? Now, to be able to do this, you need to understand what it means, right? So again, you've got 80, in this case, 80 nodes, which is a lot, and 784, right? Because that's the number of columns are coming to them. Well, that's the input. 784. But I don't want to write it like that. Okay, I like to do this. I'm going to squeeze maybe up here. Set number of columns, because that's the input. Okay, and you see that X shape down there? We can use that to actually get the number of columns. So you can do X dot shape, but then it's a tuple and it uses regular slicing. So brackets, not the 0th, but the first. Okay, That's the number of columns. I'm going to call that num calls. And then that's what the input shape should always be num calls. Now, why do I do it like that and not put in 784? Well, because this code can then work for any x, right? That's the advantage. All right. What else do we need? Oh, the num calls, by the way, has a, sorry about this. It actually is in its own parentheses, okay? And it has a comma after it. What the idea with the comma is that it makes the dimensions not restrictive. Even though this is one dimensional, in other cases it's going to be different dimensional. So that's why the comma. Okay, and then after that, parentheses, you can get a little lost in the parentheses here. And this is actually an advantage of Python, right? You usually don't have a bunch of nested parentheses, but you may be a little rusty at this. Comma, you need an activation function. Okay, the activation function is basically how do you transform the numbers to get them moving. And I can tell you that a standard is ReLU. And what ReLU does, it just takes the number as is when it's positive, but 0 if it's negative. You want to see a little picture? You type in like ReLU activation. Probably just ReLU is fine. Yeah, look at the images. And this is a nice one. You can see it says the max of 0 and z. So again, if z is positive, it's this line. You just take what z is, otherwise you take the left side. All right, so your activation, and by the way, why ReLU? Like there are different activation functions. There's like hyperbolic tangent, for instance, which is quite different. We'll look at different activation functions later. It's just gives you the best results. You wouldn't think so from this setup, but it's often performs the best. So it's become like the standard. Okay. And I believe that's all we need. Let's check. Are the parentheses closed? You can see that if you hit a parentheses, it shows you, it tries to at least, which one it connects with. And it looks like that does close it. Okay, so we've got the one hidden layer. What's left? What's after the hidden layer? Do we stop at a hidden layer? No, we need to go to the output. So we're going to add an output layer. And you do the same strategy. So it's model.add dints, but then what? What is the kind of, like, can we have any number of nodes for the output layer? No, you need to have the number of columns for y as your output layer. Now, I should say not number of columns, but number of values, number of possibilities. We know this one is 0 through 10, so we should put in there 10, okay? But there's one little piece to this that's a little complicated. And it has to do with the following. The activation function to deliver this is going to be called softmax. Okay, and softmax is like a probability function, but it doesn't actually map to kind of like 10 different, I mean, it does map to 10 different ones, but instead of using the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, it actually wants to use one-hot encoding. So let me show you what that means. We're going to go up here. I'm going to add a new text cell, okay? We want the output y to be one-hot encoded. What does that mean? So the number 2 is represented as 0, 0, 0, 1, and then 2 has a 1 in it. 3, 4, 5, 6, 7, 8, 9. I think that's right. And that's one-hot encoding too. And so you may wonder, why? What is the point of this? This seems like so extra. Well, one-hot encoding is advantageous here, especially with this type of an output, because look, 2 is not closer to 1, okay, in this case. These are bins. These are different categories. And 2 is frankly looks more like 7, right? So when you're doing like numerical outputs, you're not like trying to get, is it, well, I got a 1.8, so that's closer to 2. That's like regression. This is separate bins. And in keras, this is how you do it. you want to set it up as separate one-hot encoded vectors. So it's going to try to find a match for this one, okay? Now it's easy to code in keras, all right? It's not hard to do. So we'll do it up at the top. I'll write, so one-hot encode output y. And to do that, you need to do an import. So the import is follows from keras.utils .np underscore utils. So numpy utilities here. Import to categorical. Okay, you can see the name here makes sense because we're taking like y is a bunch of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, bunches of numbers, but actually converting them to a categorical one-hot encoding. Okay, and then once you have that, you can reset it. So now I want to call this y. I want to make some changes here. I want to do y train equals to categorical, and in parentheses we have y. Okay, so we're transforming y, and set what the number of classes should be. Okay, number of classes equals 10. Sometimes honestly, I'm not sure. Like, hey, if we don't put that in, we'll figure it out. Well, if you know it, you just put it in. Okay, that should work. And then we want to do the same with y test as well because we have y test, right? So for y test, it's to categorical y test, and same thing, num class is equal 10. You could totally reassign it. I'm gonna put everything in terms of train and test. Okay. If we're gonna do the same for x, we could call x, set x train equal to x, and we already have x test equal to x. But if you want to be thorough, you could put that into. We're actually gonna come back to x. Okay, so that looks good. Let's press Shift Enter and see if that works. Nope, got an error. To category. See, I didn't spell it right. You see that? Whenever it says it's not defined, that often means you didn't spell it right. Because you can see it's defined differently. Try that again. Good to go. And then why did I do all that? Simply so this works right. I think it's good. Yeah. So what we're going to do now, first of all, let me explain. This hasn't been fit to any data. We haven't done anything to it, okay? What we can do is check out, though, a model summary. So do this with me. Put print model summary. And really, it's like, I mean, when you initialize sequential, you're not really doing anything. But when you add the dense layers in the output, well, now you have a full structured model ready to be fit to the data. Okay, and you can look at the summary. So let's do that now. Press Shift Enter. Activation unexpected. You guys catch the error there? Let me double check code. Oh, I see. See, it's tricky with all the parentheses. It's a part of, goes like that. So it's after the number, right? And that does match what's directly above it. See where you've got the number parentheses and then activation is inside of it. So it's kind of like, think of dense as a function and all the other stuff is going inside of it. They're all the inputs to dense. Okay, fix that, try it again. By the way, errors are healthy. It's like, it's going to happen, so it's fun to look at. Okay, and here we have a summary of the model that we're going to train the data on. You can see that it has these, well, let's look at it, okay? It's got, the most important one is the total parameter, 63,000. So you can see, you get a ton of parameters in deep learning models, you know? I mean, right, think about it at the very beginning, you've got this 784 times 80. You know what I mean? Think about those diagrams, right? You have 784 nodes and they're all connecting to 80. That's 80. Well, I believe that's that number, 62,800. Check it. What is it? X shape? 784 times 80. 62,720. And then I think what they do is add like, they add 10 to it. So it's like one more. Do you see how like the last one, it's 80 times 10 is 800, but there's plus 10 because you're getting like the bias, you could say, like the plus 10. So then if you added another 80 times 10 plus 10, well, close. I shot too high. You should be able to get it exactly. 810 plus, well, whatever. They say it's 60. I'm sorry, that is the right. I was looking in the wrong place. 63,610. I was looking up here. So that's how you get that number. And then that's a lot of parameters to train. You know, you're training those, right? Those, because each of those like lines in effect is a weight. Okay. So each parameter is a weight. Look at all those weights. That's incredible. And it's going to go through and like try to figure it out. So let's do it. Okay. Let's just do it right now. Let's fit it to the data and see what happens. Okay. We don't need that code. That's just confirming it. Okay, so how do we in fact fit it to the data? Well, model.fit. I'm going to fit it on X train, comma Y train. And then you get to pick the number of epochs. Okay, now this is big. So epochs, what's an epoch? One epoch would be like you go through it all once. But that's not the thing, right? You want to go through it multiple times. Go through it once means like you're just going to take whatever random value they give you. The point is to go back and learn from the error. So how many times do we go back? Well, we'll look at a technique where we don't have to pick it in advance, but for now, I mean, we don't want this to take too long. Let's start with 50. Okay, let's see how if it goes back and randomizes 50 times, how will it do? Okay, I don't know. And then what else? At the very end, let's also look on model.evaluate X test and Y test. Okay. So we want to see, right? Well, how does it perform on X and Y? On the test set. Okay. You guys ready? This code is going to, right here, it is going to fit that model to the data that we have, matching the training values for X, all those pixels, to the Y one-hot encoded, number representations. And it's going to go through 50 rounds, basically, of adjusting the parameters to try to find an optimal solution. Okay? Then, at the very end, it'll see, well, how does it do on the test set? Okay? So let's run it and look at it. It's fun, and it may take a little time. So Shift-Enter, here we go. You must compile your model first. Oh my goodness, I left out a key step, my mistake, compile. Okay, so I got cut off with this print here. So model.compile, what is that? What's missing? You can think about that, what's missing? What's missing are some defaults that we can put in, which are, hey, what's the optimizer? Like, how's it gonna adjust the parameters? This means basically what calculus gradient descent technique? Well, Atom is optimal, okay? I don't even know the details to those. These are calculus details, okay? Just note that Atom is a good one, and we will try some different ones, okay? You also need the loss function. What's the loss? Well, right, if it's the error. And for this one, you use categorical cross entropy, which is a standard probability one. Again, we get into some technicalities here, right? These could all just be defaults. And then metrics. You can add in a metric. We definitely want to add it in. It goes in a list in quotes because it's accuracy, okay? And that way, that's what we've tested before. That's what we want to compare. It's the accuracy of the model, right? So when we look at it, we want to know, like, hey, what percentage is correct here? And when you add in the metrics, that gives you that. The reason why the loss is separate is because it's converted, it's computed from the loss, the optimizer. You're trying to minimize the loss. Okay, so you're setting up what that is as well. All right, those three, by the way, would be standard for any classification scheme with multiple outputs. Okay, and same with the softmax for multiple outputs. So it's kind of cool. We're starting with something that's not basic. It's actually multiple outputs. Try it again. Here we go. And you can see, Shift-Enter, I've got Epic 1 out of 50, so it's starting. And pretty soon it'll deliver scores. Honestly, the 80 node, there we go. Okay, now it's cranking them out quickly. And you can see the accuracy on the right side. It's getting in the high 9s, right? So loss goes down, accuracy goes up. It appears to have ended. And then what we want to know is, well, how did it do on the test set? 91.2%. Hey, for first pass through, that's pretty good. Now you may be like slightly disappointed, like, well, that wasn't as good as XGBoost, but that was actually an XGBoost tuned model. We got 90% the first time, and we're like just getting started here, okay? But congratulations, that is an introduction to keras, okay? If you want to mess around on your own, okay, and we're gonna mess around with this a lot next time. We're gonna learn how to tune keras and what we can change and not change, and what's it may be advantageous to try to change. We can't cover everything because there's so much, but hidden layers, right? You can totally like play around with the hidden layers, right? Like there was this 80, just to show you. What if we do like 40 and 40? Can we do that? Of course you can do that, right? Just copy this. One very important exception. You don't need the input shape anymore. Okay, it's going to get the input shape from the previous one. So it's kind of nice when you add a second or even more hidden layer, you just leave out the input shape and keep ReLU. So if you want to do a third one, you could do another 40. You could pick the different numbers too. Like you could go down, go to 20, right? That would be kind of cool. 40, 20, 10. Would something tighter work better? Would that prevent more overfitting? I think I'm going to try that one. I experiment. That's what you do. You experiment. Okay. Pick one more, add a second hidden layer. Let's just do that right now and then run it. Oh yeah, we get the summary. I want to put all this code together, but it should reset here. And you can see it does. And look at the accuracy. It starts off not doing as well, but will it figure out more patterns and catch up? Well, I think unfortunately we didn't give it enough of a chance, right? Note that 91.8, that's the error, not the, actually the accuracy's here, 79.6. So with more epics, that could work. And I kind of want to just try that 40-40 thing now, just to see, because we had 80 total. And, you know, I can get into the experimentation, you guys. I hope you can too. This is where a lot of the fun comes in. And yeah, you can see like it quickly it quickly gets to high 90s. But again, what's the test set? The test set didn't perform well. So this is where we need to focus on regularization. What are the techniques that we can do so this data doesn't overfit and we can get a robust model? Plenty more keras coming up.